In this lesson, we're going to look at a few theorems that relate lengths of segments within circles. The segments could be chords, they could be secant segments, and even tangent segments. So we're going to have three theorems. First one says if two chords intersect. So let's go ahead and sketch a circle here so we can see what's going on. If two chords intersect. So it doesn't have to be a diameter. The angles don't have to relate in any special way, just two chords intersect. So there's a green chord, and let's say here's this chord. They don't have to be bisectors or anything like that. No special relationship, just that they intersect inside the circle. So then the product of the lengths of the segments of one chord. So since they intersect, each chord is split up into a couple segments. So this orange one has two segments. Let's call this segment A and segment B. And the green one's separated into two chords. We'll call it C and D. So the product of the lengths of the segments of one chord, so let's say A times B, that's the product of the lengths of one chord, is equal to, so equals the product of the lengths of the segments of the other chord. So that's going to equal C times D. It's actually a pretty easy theorem to use. If two chords intersect, the product of the first two parts equals the product of the second two parts. So we'll do one example here. Number one, the directions solved for x assume that lines which appear tangent are tangent. All right, well, we don't really have tangent lines here. So we have one segment. So here's our orange segment. That's split into two parts. So that's going to be 12 times 15. And that's going to equal, and we want to look at this other segment, the two segments that this chord is separated into. That's going to be equal to 18 times x. And then we go ahead and solve. 12 times 15 is 180 equals 18x. We would divide both sides by 18 and we would get x equals 10. And that's how we use that theorem. Nice and simple. The next theorem, and all these theorems are going to have a little bit of similarities. We're going to have a product is equal to another product. So this one looks longer. So if two secant lines intersect in the exterior of a circle. So once again, we're going to have a circle, and we're going to have some secant lines, and they're going to intersect somewhere out here on the exterior of the circle. In fact, I should have done those. Let's put them in different colors here. So here's one secant line and another secant line. All right, so they intersect out there. Then the product of the lengths of one secant segment and its external secant segment. All right, one secant segment. So that's this whole thing. That's this length. So we'll call that A. And the external segment. All right, well, that is going to be this segment here, B. So A times B, the entire secant segment times the external part, is going to be equal to, and then it's going to be the same concept, is equal to the product of the lengths of the other secant segment and its external segment. So once again, we want to look at the whole thing. So we'll call that C, and then this part, this external part, we will call D. So C times D. So in words, we can say the whole segment times the outside part so this is just in everyday language. And that is going to be equal to the same thing on the other side. So the whole segment times the outside part. So sometimes that can get tricky in here, so make sure you're always plugging in the correct things. So the whole segment times the outside part equals the whole segment times the outside part. And we'll get a look at that right now. So in number 5, we have two segments intersecting outside the circle. So there's a segment, a secant segment, and then here's another one. And what we want is we want the whole green segment. This is where we have to think through this. So what is this whole segment? This is 9 plus x. The whole segment times the outside part, which is just the 9, is equal to the whole red segment. So again, we want to find this whole thing. So we have a 10 and an 8, so the whole thing's 18, times the outside part of 10. And now we can solve this. We want to distribute this 9, so we have 81 plus 9x equals 180. Subtract 81 from both sides. And we get 9x equals 99. So dividing by 9, x has to equal 11. So a little bit different, maybe a little bit harder to remember, but whole segment times the outside part equals whole segment times the outside part. The last theorem actually still fits this. It's going to look a little different, but it still fits this. And I'll show you that in a minute. This whole segment times the outside part. So if a secant segment and a tangent intersect, all right, well, a tangent never goes inside the circle, so they have to intersect somewhere outside the circle. So we have a secant segment times a tangent segment. I'll do my best to draw a tangent segment here. All right. Then the product of the lengths of one secant segment and its external part. So same idea as last time. We'll call this whole length A, and the external part here we'll call B, is equal to the square of the length of the tangent segment to the point of tangency. So this is C. So what we see here is A times B is equal to the square of this, so C squared. But notice this still does fit the idea of the whole segment for the secant segment. So whole segment times the outside part is going to be equal to, and does it still work over here? Equal to the whole segment. Well, the whole segment for this tangent segment is C times the outside part. Well, the whole segment is the outside part. So it still does work because the whole segment and the outside part for the tangent segment ends up being the same thing. So let's take a look at one example here. In this case, it fits Theorem 3. We have a secant segment and a tangent segment intersecting outside the circle. So here is the secant segment. So we want the whole thing. So that's 12 plus x times the outside part, which is 12, equals the tangent segment squared, which is 18 squared. Or you can think of the whole thing times the outside part, 18 squared. All right, let's go ahead and solve. We distribute the 12, that's 144 plus 12x. 18 times 18, I believe, is 324. And then we subtract 144 from both sides. And we get 180. 12x equals 180. Divide both sides by 12, and we get that x is equal to 15. So x equals 15. And you can use that concept to solve those last three questions there.